asymptotes. So let's say I have some function here. It's just some, I'm going to make that just a 1. No, let's make it 3. V. So I have some cubic or some square function right here initially, and we'll just make this 0. So I have some square function. P is 0, so this becomes just 1 in the denominator, so we're just looking at what the parent function is. What happens when I divide a function by another function, right? So like what happens if the denominator is 2x squared over 1x to the first? Well, x to the first divides out, giving us sort of a linear equation here that this guy is never quite getting. What happens if it's x to the second? Wow, that's cool looking. I didn't think it was going to do that. So 2x squared divided by 1x squared, we're getting an asymptote at an input of, look what happens. Let's come this way. If I plug in 50 or 5 million or whatever the case may be, when I square 5 million and then I divide it by 5 million squared here, and I multiply both of this number by 2 and this number by 1, these terms over here become basically irrelevant. They become small, so small comparatively to the size of 5 million squared that you end up getting a number that is, see, we can look, we'll trace here. These are all trying really hard to be 2, but not quite. So you can see that we're approaching 2. Now what happens if this v right here were 2? Oh, look, 2 over 2 gives us almost 1. What if this were no longer 2, but a 3? Hey, look, right there. Does that number look like it might be approaching anything for y? Yep, what it's trying to approach is 6666666, which is just 2 over 3. So that's a review of our horizontal asymptote rule. If I have square over square or cube over cube or whatever the case may be, where they match here, we're just going to take the coefficient of the largest divided by the coefficient of the largest in the denominator, and that'll give us our horizontal asymptote. So if this were -1, 2 divided by -1 gives us -2. Now, if this guy right here is 2 and this p right here is smaller, like for instance it's a 1, you have to actually divide the two functions by each other and you get something kind of icky and messy. Now, what happens if the power in the denominator is bigger? So let's say, okay, there they are being equal. What happens if this one's smaller? So now that I have something like 2 million divided by 2 million cubed, 2 million squared divided by 2 million cubed, as you get, like let's say I'm inputting 2 million in this scenario, I'm going to be getting closer and closer and closer. We're going to zoom in really tight there. Look, I'm trying really, really hard to get to almost 0. But do you notice that my almost 0 here is almost 0, but it's -0.03, -0.003, -0.0000, however many zeros, 1? You have to realize that if I take 2 and I divide it by -1 with my coefficients here, this is still going to be approaching 0 from the negative side. If I make this number positive, did you see it do its jump there where it's coming from below and then boop, now it's approaching 0 from above. So those are little things you might want to be aware of. The coefficients dividing out, even if this p equals 3, this power exponent is larger than this exponent, it is going to approach 0, but if I have a positive divided by a negative, it's going to do that from the bottom. If it's a negative divided by a negative, that'll give us that positive value from the top. So watch out for those little tiny things there. We're going to go back and finish up the notes in the next video.